This video is about finding the radius and center of a circle by completing the square. Let's start with a recap about how we can see the equation of a circle. A circle starts by picking some point to be the center. We'll choose the point right at the origin. And that will create a circle that has a radius 3. So we are going to find all the points that are 3 units away from this center. We can start by going 3 units to the right, and let's put a point there. And now let's find the points that are 3 units away from the center on the x and y axes. So 3 units up, 3 units to the left, and 3 units down. Now if we go diagonally 45 degrees, here's a line that is 3 units long. We'll put a point there. And we'll do the same in quadrant 2 and quadrant 3 and quadrant 4. Now let's find several more points. We'll continue to put down this radius that has a length of 3 units and put a point at the end. And as we do this, we're placing all the points that are exactly 3 units away from the center, that point that we initially picked. And as you can see, these points will eventually begin to create a circle. And actually, a circle is defined as the set of all the points that have a specific distance from the center. And here is our circle that has a radius of 3. Now let's pick one point on the circle. We'll choose this point right here. We know that it is exactly 3 units away from the center, and this point has an xy coordinate, an ordered pair. The x stands for its horizontal component or coordinate, and the y coordinate is this vertical distance to get to the point that we chose. Now we don't know exactly yet what this ordered pair is. We'll just call it xy, and we know that the x value is this horizontal side, and the y coordinate is the value of this vertical side, and we begin to see a right triangle. It's very important for you to understand the relationship between the ordered pair xy and these lengths. The horizontal is x and the vertical is y, and they will form the 2 legs of a right triangle, and the hypotenuse is this radius that we established at the outset. We said we're going to build a circle with a radius 3, and this ordered pair to this point is showing us the horizontal leg and the vertical leg of this right triangle. We know the radius also the same as the hypotenuse of this triangle, the radius of the circle, both the same. It equals exactly 3. Now let's bring in the Pythagorean theorem, which applies to any right triangle. The sum of the squares of the 2 legs equals the square of the hypotenuse. So x squared plus y squared equals 3 squared, just the famous Pythagorean theorem. Now whether we chose this point right here or we chose any point on the circle and gave it the coordinates xy, we could still see a right triangle where x squared plus y squared equals 3 squared. So this circle is basically made up of all the points where the x coordinate squared plus the y coordinate squared equals the radius squared. This is really where we get the equation of the circle. X squared plus y squared equals the radius squared, because the radius is the same as the hypotenuse of this right triangle that we see. Now this is a great equation for any circle that has a center at the origin, but what if we were to shift this center point elsewhere on the coordinate plane? Now remember from function transformations, if we want to shift it horizontally, let's work it down here, that would be subtracting some number of units. Subtracting h units would shift our center h units to the right. And what about shifting vertically? We would subtract some number of units from the y variable. So shifting it h units to the right is represented by x minus h in the parentheses, and shifting it k units up is represented by y minus k inside parentheses, with the exponent outside. Using the distance formula is another way that we can come up with this expression for shifting a point from the center to a new ordered pair, a new location at the coordinates hk. It still is going to equal r squared. And what we have now is a nice general form of the equation of a circle. And when it's in this form, it's very clear for us to see that the center is at the ordered pair hk and the radius equals r. Now we frequently have to deal with equations that are in this form, where we don't see our quantities squared. It's not in that standard form, and we don't readily see the radius or the coordinates of the center. So we have to apply some algebra moves to be able to rewrite this equation into quantities where we do see some factor squared. The flow is basically, it's laid out kind of nicely for us in this example. Look at the first three terms, the x squared plus 2x plus 1. Can we factor this trinomial? And hopefully you're recognizing that we have a perfect square trinomial. If you're just thinking factor, because our leading term is x squared with a coefficient of 1, we're looking for a pair of numbers that multiplied together would equal 1 and added together would equal 2, and we can see it's factored as x plus 1 times x plus 1, or x plus 1 squared. And now we do see this part that is familiar from that standard form of the equation of a circle. We have the quantity in parentheses squared. Can we see the same thing with the y's? Y squared minus 6y plus 9 is another perfect square trinomial. And a reminder is that our constant we can see is a perfect square, and the middle term would be the square root of this constant doubled. So square root of 9 is 3 and doubled is 6. You can disregard the plus minus for now. What's critical is that our constant is always positive. This middle coefficient can be positive or negative. But we see if we took this middle coefficient, cut it in half, would give us negative 3, and then square it to give us positive 9. Those are the clues that we have a perfect square trinomial. So this is factored as y minus 3 times y minus 3, or y minus 3 squared. Let's bring down the equals 25, and we can even write it as 5 squared. So it looks exactly like that standard form for the equation of a circle that is very closely tied to the Pythagorean theorem. Here's the x squared plus y squared equals r squared. We just see some constants inside the parentheses. Those are our shifts, a horizontal shift. Now remember, shifting to the right is when we see a constant being subtracted. This y minus 3 is telling us that we're shifting up 3. But since this is an x plus 1, you could think of it like minus a negative 1. We're actually shifting to the left 1 unit when we see plus 1. And we have seen that this 25 is written as 5 squared. It's a little more helpful for us to see that the radius is 5. Be cautious about this constant on the end, that our radius must be thought of as what is this quantity when it's written with an exponent of 2. So 5 squared means the radius is 5. And these constants inside the parentheses are telling us our center. It is at negative 1, positive 3, that ordered pair. So we'll go through a few more examples, but we are interested in going from an equation that is kind of has the terms all written out. How do we take some steps to see some squared factors, because that's how we're getting to the standard form of the equation of a circle. Here's our next example. This is a great example. I'll take you through all the steps one by one. The first thing to do is to really group separately the x terms and the y terms. So I'll do a little bit of rewriting, just spacing things out the way I like. Let's write x squared plus 4x, and we'll leave some space for y squared minus 8y, and then we'll have the equals 16. Now, the guiding principle here is that we need to create perfect square trinomials. This is always what we're trying to do. The way that we find perfect square trinomials is to look at the coefficient of the middle term, or this x term, and we know if you cut it in half and square it, that would give us the constant for a perfect square trinomial. So looking at our x terms, this coefficient is 4. We cut it in half to get 2, and then square that. Means that the constant to create a perfect square trinomial would be 4. And it's always going to be a positive number because we get it from squaring. So we will always end up with a positive, adding in this constant. Now it's critical that we get perfect square trinomials in order to go from this equation where we see all the terms multiplied out into that standard form which has perfect square trinomials factored. So this plus 4 is necessary, but we can't just put it in there and move on. We do have an equation, so if we decide that we needed to add 4 to the left side. We just go ahead and add 4 to the right side. And now everything's in order and we can keep proceeding. We have our perfect square trinomial, and we covered our tracks adding 4 on the left side by adding 4 to the right side. We're keeping this equation balanced. Next, we'll move over to the y variables. Y squared minus 8y, what is the constant needed to complete the square? We go to this coefficient, negative 8, cut it in half would be negative 4, and then square it would be a positive 16. So we are adding 16 to make a perfect square trinomial. And we can do that with no problem, just as long as we are adding 16 to the right side also. We're keeping the equation balanced. So now that we have our perfect square trinomials, we will write them in factored form. A quick way is, if you remember that number that we got just from cutting in half, that's the number that we see inside this factor. So x squared plus 4x plus 4 is x plus 2 squared. And with the y variables, from cutting it in half, we saw a negative 4. This is y minus 4 squared. Let's do a little cleanup on the right side and see that we have 36. So if you looked at this problem initially and saw the 16 and thought we must have a circle with a radius of 4, you can see now that that would have been a mistake. We really cannot identify the radius or the coordinates of the center until we have it in this standard form. And now we can see that this 36 is 6 squared, so our radius equals 6, and the center is at negative 2, 4. And you can always think that we go for the opposite signs when it comes to the x and y coordinates of the center. We see x plus 2 means the x coordinate is negative 2. We see y minus 4, so the y coordinate is a positive 4. So that is our standard approach to finding the radius and center of a circle when we are dealing with an equation that is in this form. Let's go to our next example. X squared plus y squared minus 3x plus 4 equals 9. We're going to use basically the same approach. We'll see a couple of interesting details that will be helpful, but what we want to do first is group our x variables and then our y variables and keep the constant over on the right side. We see a couple of terms with an x squared minus 3x. We have a y squared, but no term that has just a first degree y. We'll talk about handling that. Now, what should I do with the plus 4? It doesn't really fit in as a constant that would create a perfect square trinomial. So what I like to do in these cases is just get rid of that 4 altogether. Let's subtract 4 from both sides. So the 4 is gone, and now we have this equation equals 5. So the plus 4 is just getting in my way as I try to complete the square. I'll move it over to the other side. Now let's do completing the square. Again, it's all about finding this coefficient. We cut it in half and square it. Now, when we have an odd number, I prefer to just make a fraction over 2. So from cutting it in half, the negative 3 becomes negative 3 over 2. And when we square 3 over 2, we get 9 over 4. So our constant to make the third term in the perfect square trinomial is a positive 9 over 4. Let's be sure that we add it to the right side to keep the equation balanced. The y squared actually right now is considered to be a perfect square. We only need to find 3 terms when we have the squared term and the first degree term. So when we had x squared and a term with regular x, we needed to find a constant to be able to create a perfect square trinomial. But with a y squared and no 2y, 3y, negative y, etc., no y, no first degree y at all, we don't need to try to build this up into a perfect square trinomial. We'll leave it as is. So let's go to our 3 terms here and write this in factored form. Let's write it as a perfect square. Again, it's helpful for us to remember that the quantity that we see in parentheses is x, and then this coefficient cut in half. So we're looking at x minus 3 over 2 squared. We've written this trinomial in factored form. And if you still think I'm looking for a pair of numbers that multiplied together would equal 9/4, added together would equal negative 3, we would get to the same result. It's just a bit awkward having to work with the fractions. So remember that what we see in the parentheses is always this coefficient after we have cut it in half. So the negative 3, cut it in half, I put it over 2, and there's the quantity in parentheses. Now the y squared, it is a perfect square right now, but we do like to think of having a set of parentheses where we see the x and y coordinates. When we have a situation like this, which has just the y squared, you can think of it as being like a y minus 0 squared. It's telling us that the y coordinate of the center is 0. And it's very similar to that very first example we saw of x squared plus y squared equals 9. The radius was 3, and the center was right at the origin. So when we don't have a set of parentheses, it's as if that coordinate is 0. It's exactly as if it's 0. So we're seeing the coordinates of our center. Let's clean up the constants on the right side. I'm going to get common denominators and add these up so we see 29/4. Now don't be too hasty and call this the radius, because this is always the radius squared. If we want to talk about what is the radius, we need to do square root. So I take the square root. The denominator square root of 4 equals 2, but the numerator cannot be simplified. I'm leaving it as radical 29. So there is the radius of this circle. Square root 29 over 2 is the radius, and our center, remember opposite sign, so the ordered pair for our center is positive 3 over 2 for the x-coordinate, 0 for the y-coordinate. Let's hit one more tricky example where we have to complete the square, where our squared terms happen to come at us with some coefficients that do not equal 1. But before we get there, I want to prime you with a concept that we will be utilizing. Look at this linear equation. 3x plus 8 equals 15. If I wanted to solve this equation, isolate the variable x, I'd think first I should eliminate this plus 8. I could subtract 8 from both sides, would leave me with 3x equals 7, and so on. I could divide both sides by 3, and I have my solution. But what if we had a different equation where we were looking at something that was in factored form, like 3 times quantity x plus 8? With an equation like this, could we just go in and say, I'd like to get rid of this plus 8 by subtracting 8 from both sides? Of course, that would not work. If we wanted to solve this equation, maybe the first thing to do would be to try to distribute 3 times x and 3 times 8. And once we distribute, you can see that the number we would truly need to subtract from both sides would be 24. Now, the move that we're going to be utilizing is going to take place right here, a kind of mashup between these two moves, where I could say, you know, I can't get rid of this plus 8 with a minus 8 if I have that minus 8 in the parentheses. But would that mean I'm doing a minus 8 on the right side? No, look at what we have here. It would be 3 times x, 3 times 8, 3 times this negative 8 means it's really a minus 24. And you can see how these two equations are stating the same thing. So we're going to do some moves where we decide I need to put a constant inside parentheses. But the way that we will balance it out on the other side is to say, well, if I've just put something in parentheses, I really need to pay attention to what is the factor outside the parentheses, because a negative 8 inside this set of parentheses, which is being multiplied by 3, means that it is balanced by the multiplication, the product of 3 and negative 8. We would balance it with a negative 24 on the other side. So we will see some opportunities where we need to place a constant inside parentheses, but the way we balance it on the other side depends on what do we see multiplied to this set of parentheses. I want to give you another quick example about how this move is working. Let's say we have this example, 2x squared plus 16x equals 9. And I am interested in completing the square. We've got two terms on the left side. I'm looking for the third term, the constant, to create a perfect square trinomial. Now, when it comes to creating a perfect square, you only do it when the squared term has a coefficient of 1. We could do something like divide both sides by 2. What I'm going to do instead is I'm going to factor this coefficient out. So 2x squared plus 16x, because the coefficient is 2, I am factoring a 2 outside of parentheses. And that would leave us with x squared plus 8x in the parentheses. What does our right side look like? For now, it still equals 9. I haven't done any mathematical moves. I haven't added anything to both sides or subtracted or multiplied. All I did was just rearrange the left side by factoring out the GCF. That's critical because to complete the square, we need to have just the x squared with no coefficient right here. It's actually coefficient of 1, but you know what I mean. So now that we are ready to complete the square, we're looking here, we see a coefficient of 8. We will cut it in half to get 4 and then square it. So we know that we need, for the constant term, a 16 to create a perfect square trinomial. But we don't balance it with a 16 because this is actually a 16 times 2. So we need to balance it actually with a 32. Okay, so the 16 is needed to make a perfect square trinomial, but because we have factored out this 2, it means that to balance it, we would truly need to balance it with a 32 on the right side. The rest of this problem will be pretty similar to what we were doing with our last example. I would want to write the perfect square trinomial in a factored form, x plus 4 squared, and the next thing that we'll see us do is actually divide this coefficient out. So in this case, I have x plus 4 squared equals 41 over 2. You can tell it's not exactly a circle equation because we have only one variable. So let's get to that example right now. 3x squared plus 36x plus 3y squared minus 6y equals negative 50. So we begin by grouping the x variables separately from the y variables. I'm writing 3x squared plus 36x. I'll leave some space for that constant. Write the 3y squared minus 6y. Leave some space for the constant there. And my negative 50 is here on the right side. Now I'm getting ready to complete the square, but since we have coefficients here on x squared and y squared, I'll factor those out. Factoring out the 3 times x squared plus 12x. Factoring the 3 out as a greatest common factor. Let's go ahead and do the factoring with the y variables. Again, it's 3, leaving us with y squared minus 2y in the parentheses, equals negative 50. Again, we just did the factoring. We didn't multiply anything to both sides. We didn't change the left side at all, so we're not changing the right side just yet. We just factored. Haven't changed the value of the left side yet. But to come up with the constant to create a perfect square trinomial, doing this will start changing the value of the left side of the equation. So what is that constant that we need? We have 12, so let's cut it in half to get 6, and then square it. So we need a plus 36 right here. How is it balanced on the right side? Not just by a 36, because this is actually a 36 times 3. And 36 times 3 is 108. That's what we're adding to the right side to keep this equation balanced. What do we need as our constant term for the y's? The negative 2 cut in half is negative 1, and then squared would be positive 1. Remember, this constant always ends up positive because we get it from squaring. It's a perfect square. It's always positive. And what is the constant needed on the right side to keep it balanced? Not 1, but 1 times 3. So add 3 to the right side. There we've completed the squares and accurately balanced the right side of the equation. Now let's write these trinomials in factored form. With the x's, this is an x plus 6 squared. The y's, this is a y minus 1 squared, and absolutely in factored form we can have a negative. It's negative in the factored form when this coefficient is negative, but the constant is always positive. So this is a y minus 1 squared, and let's clean up our right side. These all combined would give us positive 61. Now the next move to get this to be in that nice standard form of an equation of a circle, we want to get rid of these coefficients. They're both going to be the same when we're dealing with a circle, so we're dividing everything by 3. Dividing every term by 3 gets rid of these coefficients. On the right side, 61 not evenly divisible by 3, so I've got it as a fraction, 61 over 3. And now it is in standard form. We can see the x and y coordinates of the center. This constant, the 61 over 3, is the radius squared. Still, remember that. So to talk about the radius, we need to do square root. Square root of 61/3. Our center is at -6, +1 as the x-coordinate and y-coordinate. And if you're in the habit of rationalizing the denominator, we'd want to take this a little bit further to get radical 183 over 3.